Hey everyone, in this video we're going to be looking at an activity on fundamentals of statistical models. So in this activity, we're going to be looking at some key concepts related to statistical models and predictive modeling that are necessary for having a good understanding of the different types of variables that we're working with and their roles in the models that we're using. So to start from a broad perspective, looking at statistical models and predictive modeling, George Box, a famous statistician who used to be a professor at University of Wisconsin-Madison, has this famous quote where he says, essentially all models are wrong, but some are useful. And what Box was getting at here is that regression models, logistic regression models, all of these kinds of statistical models that we'll be learning about are oversimplifications of reality. They're all technically incorrect in the assumptions that they make, the patterns that they assume are true, but that does not mean that they're not useful, right? It's that by oversimplifying things, we are able to make pretty good guesses that are not always perfect. So sometimes they're wrong, but the goal is to make a predictive model or a statistical model that is useful, even if it's not perfect. So that's one aspect to keep in mind when using these statistical models and fitting them, that we're sort of oversimplifying reality, but in a way that is useful to us, hopefully. And Kathy Pham, a data scientist, has this quote on a separate issue. She says, today's computer scientists write code with the potential to affect billions of people's privacy, security, equality, and well-being. So when we're using predictive models for the company that we work for our own endeavors, it's good to keep in mind the impact or the effect that the results of the models can have on others if it's affecting decision making, especially in contexts like medicine, medical care, things that affect people's lives, right? So, of course, if you're modeling outcomes of like sports games, this is not what Kathy's getting at here. She's saying in situations where you're, say, developing novel drugs, investigating patterns in like cancer incidents, those types of things, it's good to keep in mind the perspective of how the insights generated from our models will affect people. And hopefully we all can do that in a positive way. Okay. There are bad uses of predictive modeling that can harm people, right? And there are good ways in which we can use it. We can use it to develop better treatments to help people live happier, longer lives. But we could also, some people unfortunately maybe use it to maximize the effect of something like influencing, seeing which marketing strategies influence your doctor to prescribe which drugs to one patient or another as a marketing strategy rather than what's optimal for the patient. Okay, so there's different uses of predictive modeling in many contexts, but it's good to keep in mind the ethicalness, the ethics of using these properly. Okay. So getting into variable types and some scenarios here, looking at variables and how they interplay with predictive modeling, we can consider a few examples here. So a common setting for a company like Zillow or any other website that's estimating housing prices is to predict the selling price of a house that has yet to be sold here. Okay. So we likely have characteristics about the house, like its square footage, how many bedrooms it has, and the year it was built. Okay, so we could use those characteristics in a predictive model to get a estimated selling price or predicted selling price. Another thing that we can predict that's often of interest, for example, is the national unemployment rate. So this is a unique type of data because it typically consists of, unlike the selling price, where maybe a house sells just a couple of times ever, the national unemployment rate is something that we observe repeatedly many times across time. And so this is what we refer to as time series data, repeated measurements on the same thing. Time series data require or necessitate specific types of predictive models that we won't cover in this course. But the types of things we learn can still be used for time series data. They're just not optimal. But in this time series data where we have repeated measurements on the same thing, often a good predictor is the previous values of that same variable. So to predict the unemployment rate next month, it's going to be a really good predictor what the unemployment rate was this month, which maybe sounds obvious, but that's an aspect of time series data. And of course, we can improve upon that with additional information as well, but that's always a good starting point. Another example of a predictive modeling scenario that likely affects you every day, if you use Gmail or Microsoft Outlook, Microsoft and Google will try to estimate if the email is spam or not. Okay, this is an uncertain thing. You can't definitively know if something is spam or not. So Google has to use characteristics, and Microsoft uses characteristics about the email to essentially assign a probability that they believe that email is spam or not. And they might use characteristics like the number of consecutive capital letters. Okay, spam emails likely have many capital letters, or emails that have many capital letters are likely spam consecutively, but not necessarily. So there's other factors, of course, as well that affect the likelihood of an email being spam. Like, is the sender in your address list? Have you ever corresponded with them via email before? Many factors like that. Google likely has a much more complicated model using many factors than just this, but this is an example here. Okay. So as we're completing this activity, when we hit these blue checks, we'll type a response in so that we can submit this document via Blackboard for credit, no credit. Okay. So when looking at these scenarios, some key terms that are important to understand are what we call observational units and variables. So observational units are the things on which data values are recorded, whereas variables are the characteristics that we are recording about the observational units. Okay, so in the scenario above, for the housing prices, the observational units are each individual house. So collectively, many observational units make up our data set. For number 2, the unemployment rate scenario, the observational unit is, if we're describing the unemployment rate, that's something that is measured about the United States. So I would say each country, if we were looking at the unemployment rate across many countries, if we're looking at just the US, let's say this is monthly. If this is monthly, then each month would be the observational unit. I think it'd be reasonable to say that the United States, you could say the measurement is actually on the United States, like we're describing the unemployment rate of the United States. So I think that could be acceptable as well here. Certainly, if you had multiple countries of data, the observational unit would be the country instead. But I think here we're getting more at just a single country. Okay. So number 3, if an email is spam or not. Okay, so our observational units in this case are each individual email. Okay. That's what we recorded things about. So that's what our observational unit will be. And we can also have the variables for each of the settings, each of the scenarios. Okay. So the variables for the first scenario are the characteristics that we measured about each house. So in this case, we'll say the size, number of bedrooms, and the age of the house are the variables. And for the second scenario, the variables are the unemployment rate. That's what we are measuring about each month or each country, depending on how the data was structured. Okay, and then the last one for the email setting, our variables are whether or not each email is spam. And the other variable is the number of consecutive capital letters in the email. Okay. So those are our observational units and variables for each of the scenarios. It's important to be able to define these because in order to obtain a representative sample of the population that we're interested in, of the larger group that we're interested in, it's important that when we are selecting observations for our sample, we introduce randomization when we can, typically at the level of the observational unit. So for example, if we want to understand the relationship between the square footage, number of bedrooms, and age of a house and its selling price in Grand Rapids, it'd be important to understand that our observational unit is each individual house in Grand Rapids. So then we need to randomly select from all houses in Grand Rapids several homes. Okay. And then similarly for, it would be a little bit more difficult to obtain a random sample for the unemployment rate data, but for the emails, if we were interested in emails, then we'd be introducing randomization and constructing our sample by randomly selecting emails from the population of emails that we're interested in. Okay. Okay, so we kind of answered both bullets there, observational units and variables. And so we can move that, I guess. Okay. So those are two key terms, observational units and variables. Another important aspect or thing to understand when conducting predictive modeling is the different types of variables that we're working with. This is important to understand well because we have different types of predictive models that we can use, and the appropriate statistical model, the one that will perform the best or that is valid to use, often depends on the types of the variables that we're working with. Okay. So generally, for the most part, although there's other subcategories, variables are either quantitative or categorical. So quantitative variables, and then here we have the subcategories, which we'll talk about for each of those types. So quantitative variables are variables such that arithmetic is sensible. So we can conduct addition, subtraction, multiplication, or division on the values in a sensible way. Within quantitative variables, we have two main subtypes for this class, is how we'll define it: continuous and discrete quantitative variables. So continuous quantitative variables can always be measured with more precision. So in other words, you can always measure the value out to more decimal places if you wanted to. Some examples of that. We look at down here, someone's height in inches. You could measure that you are 68.2 inches tall or 68.24 inches tall. You can always measure it out to more decimal places. So that's what makes it continuous. It's a similar thing for someone's weight or someone's age in years. Even though age is commonly recorded as a whole number, saying I'm 30 years old, technically you could measure to say you are 30.24 years old or 30.247 years old. You can measure that more precisely. And so because you can measure it more precisely, that's what makes it a continuous quantitative variable. It doesn't matter that in a data set it's reported in whole numbers or not. It matters how it could be measured. Okay. The number of pets that someone might have, that's an example of a discrete quantitative variable. So discrete means it must be in whole numbers. Okay. So you can't have 1.5 pets. You can't have 1.52 pets. You have to have either 0, 1, 2, 3. Okay. So these are must be whole numbers. So those are the types of quantitative variables that we'll deal with. We also have categorical variables. And the two main subtypes of categorical variables are ordinal and nominal categorical variables. So categorical variables are not sensible to use in arithmetic operations. So they're things like your favorite color being red, blue, green, or yellow. The favorite color is a category. It's a categorical variable. Within categorical variables, we have these ordinal variables in which the categories have a logical or set ordering to them. And then we have nominal categorical variables, which have no particular ordering to the categories. Separate from ordinal and nominal, any categorical variable can be binary if it has two possible categories. And note that an ordinal variable can be binary, but it doesn't have to be. And a nominal variable can also be binary, but it does not have to be. Okay. So let's look at some examples. So measuring someone's genotype, where maybe they have no minor alleles, one minor allele, or two minor alleles. Okay, these are, say, three different outcomes of a genetic variant. And there's three categories. There's a particular ordering to them. And so this is an ordinal categorical variable. You can also look at Netflix subscriber status. So whether or not someone subscribes to Netflix. That's binary because they either, yes, do subscribe to Netflix or they don't. And it's nominal because there's no correct ordering to the categories. You could have no and then yes, or yes and then no. Okay. Class standing. So whether a student is a freshman, sophomore, junior, or senior, this is categorical. And there's a particular correct ordering to these categories. So that's what makes it ordinal. Okay. So let's look at some maybe a little bit trickier examples. So what are the types and subtypes of the following variables? So what if we had the rating of agreement? This is a tricky one that many people treat as quantitative in practice, but really it should be ordinal. Sometimes it's even reported as on a scale from 1 to 5 for rating of agreement. The reason this is still categorical, so this is categorical and ordinal because there's a particular ordering. The reason it's categorical, not quantitative, is because you can't take 4 as the amount of agreement and say that's twice as much as someone who rated a 2. All we know is that 4 was more agreement than someone who rated a 3. And we just know the relationships between categories like that. And that's the same logic here for roller coaster intensity. So this is categorical and ordinal. Yeah. So if we have a roller coaster that's rated a 5 on an intensity scale, so for example, if you go to Canada's Wonderland, which is the largest theme park in Canada, in Toronto, the roller coaster intensities there are rated on a scale from 1 to 5. Not 1 to 10 as I believed when I went there the first time and rode a 5. So if you have roller coaster intensity being 1 to 5, 5, a roller coaster that's rated a 5, we know is more intense than one that's rated a 4. But we can't say, for example, that a 4 is twice as intense as a 2. We don't know that for sure. We just know that the particular ordering holds, but not the multiplicative degree of intensity necessarily. And also, it doesn't make sense to say that you take a 5 roller coaster, subtract a 1 roller coaster, and that's exactly equal to the intensity of a 4 roller coaster. That is not necessarily true. Okay? And also not sensible in a way. So the last thing we'll look at. Okay, so the probability of each NFL team winning the Super Bowl this year. Okay. So this is quantitative because we could have a probability of, say, 10% that the Lions win the Super Bowl this year. And maybe there's a 5% chance that the Green Bay Packers win the Super Bowl this year. We can indeed say that the Lions then have like a twice as high chance of winning the Super Bowl this year. We can compare them multiplicatively like that in a sensible way. Okay. So this is quantitative, and then probabilities can be measured more precisely always. So this is continuous. All right. And the last thing we'll look at is the different roles that variables play in predictive models. So the types are important to understand because there's certain types of models for a categorical outcome, and there's certain types of models for a quantitative outcome. Then when we're actually fitting a model, even once we've selected a model, it's important that we're able to designate or decide which one is our response variable and which one is our explanatory variable. Okay. So the response variable is the outcome that we are trying to predict or trying to understand the relationship of the other variables with. The explanatory variable is our predictor. It's what we're using that we think is informative of the outcome of interest. Sometimes these are called predictor variables, covariates, independent variables. There's a lot of different names for explanatory variables or predictor variables. In predictive modeling, predictor is the most common name. But in statistics more generally, it's called explanatory variable. All right, so let's think about what are the response and explanatory variables if we had this setting where we were exploring whether a student was accepted to a university or not, where we know their GPA and their ACT and SAT scores. Okay. So in that case, the response variable is going to be whether or not the student is accepted to a university. And then the explanatory variables are GPA and the ACT or SAT scores. These are what we're using, and we could try to predict. We could use these to try and predict the probability of, say, a student being accepted to university. And then we can also think about the types of these variables. So in this case, whether or not a student is accepted to a university, this is a categorical variable, and it is you could argue ordinal if you say being accepted to the university comes after not being accepted, I suppose. I would say most people would consider this to be nominal. Okay. Categorical, nominal, because there's no particular ordering to the categories. And then it's also binary. There's two possible outcomes. The student is accepted to the university or they are not. Okay. And then for these variables, we have GPA, which is a quantitative and continuous and the ACT or SAT score, which is definitely quantitative. I've never taken the SAT, but I believe it comes in whole numbers. So technically, that is discrete. And I believe the ACT only comes in whole numbers as well. Unless it's changed, but I've been out of high school for a long time. So if you could measure it, I guess like a 28.42 on the ACT, then it would be continuous, I guess, but I believe it comes in whole numbers. Okay. And lastly, let's look at these scenarios. So the response and explanatory variables for each of these. Okay. So we have the selling price of the house example. In that case, the response variable is the selling price of the house. The explanatory variables are the size, number of bedrooms, and age. That's what we would use to predict the selling price of the house. And the response variable we can say is the monthly unemployment rate here. And in this case, this is where it's a unique scenario because it's time series data. The explanatory variable is also the monthly unemployment rate. We could say the previous month's unemployment rate. And we could say next month's unemployment rate. And then for the last example, email being spam or not. So the response is whether or not the email is spam, which is categorical, nominal, and it's binary. And the number of consecutive capital letters is our explanatory variable. Which is quantitative. And is it discrete or continuous? So the number of consecutive capital letters must be discrete. It has to be a whole number. Okay. Unemployment rate, these would be quantitative and continuous. You could measure the unemployment rate more precisely if you wanted to. Selling price of a house, technically that would always be in whole dollars, but I suppose there is a way in which somebody could sell a house for a fraction of a cent, I think. So I would argue that this is continuous, and anybody modeling this type of outcome would always treat it as continuous. Arguably more important here. Sometimes it's good not to get too bogged down in the technicalities of things because people would always use a model that is for continuous outcomes when predicting this type of thing. And size, number of bedrooms, and age. Okay, so size is going to be square footage, so that would be quantitative and continuous. The age in years, quantitative and continuous because we could measure that more precisely. Number of bedrooms, though, that would be an example of a discrete quantitative variable. It must be a whole number, right? So that's it for each of these scenarios. And that's a quick, brief overview of fundamentals of statistical models.